All right, so because we have this normalization, alpha squared plus beta squared equals 1, we can define our quantum state in terms of polar coordinates, or we can use this 3D sphere, so we can go back to our spherical light switch. And so I have sort of the polar coordinates defined here relative to Cartesian axes. And so we have some angle theta, which is measured away from the z-axis, and we have some angle phi, which is away from the x-axis. And so if I rewrite my quantum state in terms of polar coordinates, it would look something like this. So we have our quantum state equals cosine theta over 2 times 0 plus e to the I phi sine theta over 2 times 1. So this thing is called the Bloch sphere, and as we're going to see, it gives us kind of a physical place to go back to when we get confused about what our qubits are doing or telling us, or where how they're being manipulated. I find it to be a very useful tool, and I think you will as well. So we know that classical bits store only two values, 0 and 1. And we can combine them in large units to store greater ranges of values. And the question is, how much information can a qubit store? So the whole sphere is kind of my qubit, right? There's technically an infinite number of points on this unit sphere, right? So in principle, I could sort of store the entirety of Shakespeare in this one qubit. But that's kind of misleading because this single qubit will give either 0 or 1 when I measure it. So from a single measurement of a qubit, we only get a single bit of information about the state of the qubit. This was sort of what I was trying to say, but maybe a little bit more, less elegantly before. But how much information is represented by a qubit if we don't measure it? That's kind of the question. Well, it's kind of a trick question, because how much information can be represented by a qubit if we don't measure it? 0. I mean, you eventually have to measure it to learn something about it. But there's something really important in that trick question, because when nature evolves a closed quantum system of qubits, she keeps track of all the continuous variables that describe each individual state, like A and B or theta and phi. And so there's all this hidden information. And what we'll see is that this hidden information grows exponentially with the number of qubits. So instead of having a binary system with our typical logic bits, in qubit land, we have this system that grows exponentially. So for every qubit, we should be able to take on the values of 2 to the n bits. So if we have n qubits, we should be able to take on the values of 2 to the n bits. Because let's think about 2 bits, 0 and 1. I can have 0, 0, I can have 0, 1, I can have 1, 0, or 1, 1. And 2 qubits could take on all of those values at once. So 1 qubit can take on the value of 2 bits, 2 qubits can take on the value of 4 bits, and in general, n qubits can take on the value of 2 to the n bits. All right, so if you start looking at tables like this, which kind of show like numbers of qubits versus like compute time, so this particular table is assuming times based on a classical computer with a clock speed of 3 gigahertz. So that's 3 billion operations per second. So that's kind of a typical computer, classical computer. So if I have 1,000 qubits, that can store the same number, the same amount of information as 10 to the 301 bits. 10 to the 301, that's a wild number. So let me think. That's like 3 universes worth of hydrogen atoms. It's a humongous number. And the amount of time that it would have taken a classical computer to do that calculation is 10 to the 284 years. So the age of our universe is like 13.5 billion years old. So this is much, 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 much longer than that. So 1,000 qubits isn't even the end of what could be possible. If you kind of look at state-of-the-art quantum computers that have been built by people like Google and IBM, they have reports of systems with 50 and 75 qubits operating together, maybe not without faults and errors. They're not quite to 1,000 yet, but it's early days, right? And so we could imagine getting to systems with some of the platforms we'll talk about that could get us to several thousand, maybe tens of thousands of qubits in a single device. And yeah, the amount of computing power you could have at your fingertips with that is pretty astronomical.